Okay, here we have section 2.1, and we want to go into floating point numbers a bit. So, this is in, math and arithmetic kind of stuff. We are working with real numbers is the idea. That's what we're trying to work with anyway. Things like 1.379 and pi and etc. Okay. Now, so you need to kind of have some idea how floating point numbers work. Now, they're typically they would be actually represented in base 2. We'll look at them in base 10, since that's what we're familiar with. And so if you think of a number in scientific notation, because that's how they're going to be represented within the computer, actually. Okay, you might have a number like negative 1.274 times 10 to the negative third or something like that. Now I put in the negatives to point out that we'll need a place for the sign. Now, so if you're told you have an 8-bit word to work with, or you've got 8-bit architecture or something like that. Now, typically, we're talking 64-bit, 32-bit, 64-bit, that kind of thing. But that's actually base 2, and so 8-bit base 10 is right up there with 64-bit architecture, I think. I'd have to think about it a little more. And like I say, we're not trying to get too technical here, but we're trying to see what one needs to worry about. So to represent that number with those 8 bits, I'm going to need some room for the sign, right? That's got to be a plus or a minus. And now don't worry about the decimal point. We'll just realize that when we look at these, we're looking at a decimal point. So here are my 4 digits, 1, 2, 7, 4. And so now I've used up 5, and suppose I'd like to be able to go up to like 10 to the negative 99th or 10 to the positive 99th. Then again, I'm going to need something for my exponent sign, a plus or minus. And then suppose I need 2 digits for the exponent, and here it would be like 0.3, something like that. There I've used up 8 bits. Okay, so that's all the room I have. Now, so as we look at that, what are the first things that come to mind? Well, not all numbers can be represented. Okay, so here I'm I'm representing 1.274 times 10 to the third, or well, actually it was 10 to the negative third and negative 1.274. But what if I need a five digits, right? I can't represent that. So I can only represent 5 significant digits. So the number 1, 2, 3, 4, 5, as far as this computer would be concerned, is equal to, well, this is a problem with the 5 because you get into funny rounding rules and all that. But let's say it would get rounded up. Then, it's equal to 1, 2, 3, 4, 6, and it's equal to 1, 2, 3, 4, 7, right? There's no difference between those numbers as far as how I can represent them. That is if I had rounded up. I guess these would all round up to 1, 2, 3, 5. Right, so we'll say equals 1, 2, 3, 5. Okay, so I can't, I'll put a decimal point on those, like that. Then, all those numbers, sorry about that. All those numbers would end up having to equate to 1, 2, 3, 5. So I can't represent all numbers. Along those lines, I would have a smallest number. Now this is an absolute value because I can always put positive or negative signs on things, but a smallest number. And depending on exactly how strictly the computer can hang on to things, let's say it's always got to have a non-zero digit here first. So my smallest number would be 1.000 times 10 to the negative 99th. And my largest number would be 9.999 times 10 to the positive 99th. Okay, so that would be the best I could do. If I needed bigger numbers than that, I'm sipping some hot chocolate here, sorry. I'm out of luck, or if I need a number closer to 0 than that smallest number, I'm kind of out of luck. So when I say smallest number, that's smallest non-zero number. Okay. And, back here, I did not. So, I guess this sign makes sense. The exponent sign and the exponent number, that all makes sense. This stuff in here, I've always called it the mantissa. That is a word for it. But another word for it is significand. Significand. Okay, and you would want to know how many digits you can carry in that mantissa. So right, we said, we've got 8 bits. So you'd think, an 8-digit number. Well, no, not 8 digits, just 4. And because we have to keep track of some other things in there. Okay, so some of these implications and problems would be we have a smallest possible positive number, we have a largest possible positive number, and beyond that, even between those two numbers, we can't hit every single number. So certainly any numbers, any numbers that would, in this particular machine that I'm talking about, any numbers that would take more than 4 consecutive non-zero decimal places to describe can't be represented. So pi cannot be represented exactly. Square root of 2, 1/3 for that matter. Okay, so not all the numbers are there, and in particular some very easy numbers. So 1/2 is there in this case. Well, actually in base 2 it is as well, but 1/2 is there since 1/2 is equal to 5.000 times 10 to the negative 1. So I can represent that just fine. 1/3 is not, because 1/3, the best I could do would be 3.333 times 10 to the negative 1. 2/3, similar, is not, because that would be 6.667 times 10 to the negative 1. That's as close as I could get to 2/3. Now, in actuality, numbers like 1/10, so in base 2, so in a real computer, 1/10 is not there. You think it's there, but it's not. Okay, because I cannot represent 1/10 as a non-repeating decimal, so to speak, binary decimal, in using base 2. Can't be done. So actually numbers that you would think are really nice and easy that are there, no, it's not actually there. So you think you're putting in 1/10 or 0.1, but it really doesn't. It goes in as a number very, very close to it. Excuse me. Okay. So we have to approximate a lot of numbers. Now, because of the smallest and the biggest, we can have a couple things. Because we have a smallest number, we can get underflow errors. Excuse me. Underflow error, and that is when we try to use a number smaller, and of course I don't mean 0, so smaller than the smallest number. Okay. Now, in general, not a big problem. Usually you'll get an error message, but it's not a big issue. As typically we just substitute 0. Okay, because it's really close to 0 anyway. But it's good to get that error so that you were trying to use a number that was very close to 0, but we couldn't actually do it. And then there's an overflow error. And that is when we try to use a number bigger than the biggest number. Okay. And again, I'll say typically. So typically, this is fatal. Okay, if you're trying to run a program and you do this overflow error, it will stop. Now, within Python itself, I've played a little bit with this, and actually, I'm not sure exactly. Python 3 seems to handle numbers bigger and smaller than the max and min. So in other words, the language itself seems to sort of catch it, catch those errors and compensate for them. And to tell you the truth, I'm not sure exactly how or what it's doing, but there are plenty of computer codes that can do so plenty of languages. Now, by plenty, I don't know, at least half a dozen anyway. Plenty of languages allow for arbitrary precision numbers. So in other words, you can set it possibly yourself and say, oh, I don't want to allow anything bigger than this, or I want to allow really, really, really big numbers. And so, those languages are set up to do that. Python 2 did not allow any of that sort, didn't handle the max and min. But it appears to me that Python 3 does handle that. And so, those might not be as big a concerns with Python 3. So, but it's good to know for any given language, yes, those might be a concern. Now, what else? The other, and this is definitely a concern. Okay, a definite concern is addition or subtraction. It really depends on the signs of the numbers as we talk about them, but really it's the difference. So really the difference is what we're talking about. Well, no, it's really, we'll say addition, subtraction of very similar and very different sized numbers. Okay, now let's look at an illustration of that. So suppose I have a couple of numbers, and we'll look at what does the computer do if it adds or subtracts these things, this kind of stuff. So suppose what I want to do is add the two numbers 1.234 times 10 to the 2 plus 1.234 times 10 to the negative 3. Okay, now what's the computer going to do in actuality? Well, it carries the 4 digits here, but when it actually goes into, we looked at there's the CPU and the accumulator and so forth. When it actually goes into the accumulator, it's going to give us twice that many places. So we'll actually have 1.2340000 times 10 to the 2 plus 1.2340000 times 10 to the negative 3. Well, now the first thing it's going to do is get these exponents the same, and I believe it should change that one to 10 to the 2. So, what's this number if I change it to 10 to the 2? All right, so I'll have 1.2340000 times 10 to the 2, or in other words, that's 123.4. And now I add to that, well, actually, let's make this, just make it a little easier, 10 to the negative 2. So I don't have quite as many zeros. Now, so to write this as times 10 squared, I have to move that decimal place 4 spots to the left. Right, so this number is going to be 0.000 1, 2, 3, 4, and that's 1, 2, 3. Yeah, okay. I think I have that correct. Right, because if I this original number is actually right 0.01234, and this, if I multiply this number by 100, I'll get up here to 0.0124. So I can check my work, and that looks good. So I'm going to add those two numbers. So let's put them vertical now. 1.234 times 10 to the 2. Well, let me get those extra zeros in there. So this is what the accumulator will do. So it will handle that non-standard form there, with starting with the 0 and so forth, and have the 0 padding, and then plus 0.000123 times 10 to the 2. We add that and we get 1.2341234 times 10 to the 2. Okay, but now the accumulator takes this part, really it's just that digit, and rounds, and so the answer becomes 1.234 times 10 to the 2. So we see, oh yeah, that's a problem. I just added these two numbers, and they were enough different in size that I ended up getting this answer, which is correct to those 4 decimal places, but you see, basically it didn't add that. That number was never added to this as far as the effective outcome here, and so that can be a problem. And so we try to avoid doing that sort of thing. And similarly, when you subtract two numbers that are very close in size, you can have some things like that happen. So, for instance, in the accumulator, if you're working inside the accumulator, and so you've got the extra digits, and you end up taking, say, 1.234 5 minus 1.2341, right, we'll get 0.0004. But what could happen, and a lot depends on just order things are happening and done and so forth, but what could happen is it could lop that off, right? You might think that, well, what it would do is just then make that a point, a 4 point something times 10 to the negative. It's possible that within the accumulator it could do something like that, but it's also possible that it would just round down and call that thing 0, and so you can end up dividing by 0. Say I needed to divide by the difference of those two numbers. Well, I might end up dividing by 0 even though I'm not. And so, again, you just have to be careful about that sort of thing. And so, implications here of all these things. Well, again, for us within Python, the overflow and the underflow, and in general, there's not a lot we can do about that. Those things, or the fact that we can't represent every number. There the implications are pretty straightforward. You just have to realize that you'll get errors that are not the fault of your algorithm, not really the fault of the computer, in the sense that, well, what computer you're working with and so forth. They're, in that way, no one's or nothing's fault. They're just going to be errors because it's the best we can do. But implications we can deal with are things like, suppose I'm going to add a list of numbers. Well, adding a list of numbers is best done smallest to biggest. Okay, so in other words, if I want to add, say, 1 over 1,000 plus 1 over 100 plus 1 over 10 plus 1, this is better than 1 plus 1/10 plus 1 over 100 plus 1 over 1,000. Okay, so, and you can see the issue is that here I'm starting with the smallest and I'm adding something as close as I can to it. So they should do okay when I add them up. But in this bottom one, I'm making a bigger and bigger number, and if this number here is too big, I won't see the result of adding that one to it. And so it, an implication is, if you have to add a list of numbers, and here I'm doing positive, if they alternate, if they've got different signs and so forth, well, then you need to be Also careful that way. I'd probably add the negatives and the positives separately, and then take the difference of the two. But as far as these positive numbers, I would go smallest to biggest. And then also, as best you can, avoid subtracting two numbers that are very close in size, or adding very different sizes. And that goes to the summing up above there. Now, you don't really want to subtract numbers that are greatly different size either, except, well, sometimes, sometimes you will just have to, but that's not quite as worrisome because, well, the big number was so much bigger than the other one. Yes, you subtracted. That would be nice to know that you got the right answer, but if they really are that close, that far apart, then again, it may not matter that you didn't really change the number much. So we, for this, we looked at a particular set of numbers to add there. An example here of avoiding things when you can is consider two forms of the quadratic formula. I bet you didn't know there were two forms of the quadratic formula. Okay, but yes, really there are. So, form one, you're starting with this, ax squared plus bx plus c equals 0. You complete the square and all that kind of stuff, and you've seen this kind of thing before. You get x equals minus b plus or minus the square root of b squared minus 4ac over 2a. But now form number two. Now if x isn't 0, that's a slightly different case, but if x isn't 0, now if c is not 0, I know that x isn't 0. So so as long as I have a c there, I know that x isn't 0. So I can divide through both sides of this equation by 1 over x, or divide through by x squared. And then I could write this, c times 1 over x squared plus b times 1 over x plus a equals 0. Now you can go through the mathematics of this, of just using the quadratic formula here, saying something like, well, let u equal 1 over x, and you redo this quadratic formula, swapping out the a and the c. Okay, because that's all that we've done, is if I let u equal x. Well, then you see that would say that 1 over x is equal to minus b. Now, here's, again, this is a subtle thing. I'm not too worried about going into the, the algebra of it all, but it would actually swap upside down the plus and the minus. In some ways that doesn't matter at all, but it will to us. So you still get the 4AC, because when I swap out A and C, it doesn't matter there, but you get a 2C here. And so that means that X equals 2C over minus B minus or plus the square root of B squared minus 4AC. And like I say, I bet you didn't realize that. But let's look at that. Let's see, I have an example here somewhere. Okay. You know, suppose I have 2x squared minus 2x minus 24 equals 0. So A equals 2, B equals negative 2, and C equals negative 24. Then in the first case, if I write this as x1, x2, I get 2 plus, we'll do the plus first, square root of 4 plus 192 when you multiply and square and so forth over 2a, so that'd be 2 times 2. That ends up being 2 plus 14 over 4, or 4. And you could factor this thing up here and see that one of the roots is 4. Similarly, we have 2 minus the square root of 4 plus 192 over 2 times 2. So that's 2 minus 14 over 4. And you get negative 3. So there are my two roots. Now, here's where, using the second one, I did I swapped the minus and plus. So again, this is 2c, so 2 times negative 24. And then over that same, b, minus b and plus or minus, except it's minus plus, so we do the minus one first. So we'll get 2 minus the square root of 4 plus 192. And so this is negative 48 over negative 12. And so notice, see, we get 4. It's that same x1 if we use the minus here instead of the plus. And now if we use the plus, 2 plus 4 plus 192 equals negative 48 over 16, and so we get our negative 3. And so you see, we get the same answers, but the big difference here is that if our b is negative, okay, if b is less than 0, what I'd like to do is, since that'll make that number positive, and we'll do a plus here, so I'm adding two numbers. I'm not finding the difference of two numbers. Adding two numbers that are really usually, as best as we can do, relatively close in size. Here, 2 and 14 don't look that close, but, actually they're not bad. So if b is less than 0, we'll compute x1 from 1, whoops, and we get to use that same plus down here if we do the x2. So x2 from 2. And I'm going to do another video where I just go through this and show that if the numbers are big enough difference, we do have a problem. Well, actually close enough to the same, I guess. we do have a problem. And then if b is positive, what we would do is we would calculate x2 from 1 and x1, the other root, from 2. Because if it's positive, then we would actually have a negative number here, and so we get a negative and a minus number, so it'd be kind of like adding, and those would be good things to do. And so that's a very real implication with say the quadratic formula. So we change up our algorithm to make this work better. So I will have an accompanying video where I look at, I'll calculate an x1 from something kind of like this, but much more exaggerated. So I'll calculate an x1 and then calculate an x2, these two different ways, this way and this way. And we'll see that if we stick with both of these, one of the two is going to be a problem. And in my example, it's going to be the second one. But that is an introduction and just kind of an overview of how floating point numbers work, and the fact that we do actually have to be cognizant of the fact of how floating point numbers work, because there are some real implications to it. Okay, call that done.